All right, here we go with another installment of the Special Topics video series. This is Special Topic 13, Data Tables. Specifically, we're going to work on the problems that are on pages 81 and 85. What you're going to experience with these data table questions, I picked them because, number one, they both feature, a data table. But then they mix in together, and I think quite beautifully mix together, lots of different ideas from across the curriculum. You're going to see some Riemann sums, you're going to see some tangent line approximations, you're going to see some related rates. Lots of different ideas are going to come together in these two problems. So buckle up, and here we go. Okay. So this first one came from the 2007 AP exam. It's question number 5, and it's calculator inactive. Okay, we're told that the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function. Twice differentiable just means the first derivative exists and the second derivative exists. So first and second derivatives exist. Not sure why that's important yet, but I'm sure we're going to find out. T is measured in minutes. For the interval 0 less than t less than 12, the graph of r is concave down. Okay, more information coming our way. The table above gives selected values of the rate of change, r prime, of the radius of the balloon over the time interval 0 to 12. At time t equals 5, the radius of the balloon is 30 feet. Okay. Note the volume of a sphere of radius r is given by volume equals 4/3 pi r cubed. It's pretty typical that the College Board will give you volume formulas. You're not expected to memorize those. If you know it, great. If you don't, that's okay too. All right, here we go. In part A, estimate the radius of the balloon when t is equal to 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give a reason for your answer. Okay, so tangent line to r at time t equals 5. Well, you know we need a point and we need a slope. At t equals 5, do we know what the radius is? Yeah, we know that the radius is equal to 30. What's the slope? Well, the slope is going to be the derivative of the function at time 5. I can go to my data table. At when t is equal to 5, r prime is equal to 2.0. Okay. Your tangent line equation, L of t, is going to be 2 times t minus 5 plus 30. Your slope times t minus the x-coordinate for your point plus the y-coordinate for the point. Okay, so far so good. They want the approximation to the radius at time t equals 5.4. So r of 5.4 is approximately what you're going to get using your tangent line to approximate the point at 5.4. So that's 2 times 5.4 minus 5 plus 30. There's nothing in here that says that you need to indicate the units, but what would the units be for the radius? That should be feet. If you want to live dangerously and simplify this, you can. 5.4 minus 5 is 0.4, times 2 is 0.8, plus 30 is 30.8 feet. We've talked about this repeatedly. There's no need. There is absolutely no need to simplify. Now, we still need to determine whether our estimate is an underestimate or an overestimate, and we've encountered this in some of the other videos that I've filmed. You need to know about the concavity of r. How is the graph bending? If your graph is concave down, then all your tangent lines are above the graph, and you get overestimates. If your graph is concave up, your tangent lines are below the graph, and you're going to get underestimates. Well, do we know anything about the concavity of R? Go back and read the question one more time. The graph of R is concave down for the time interval 0 to 12. Well, what I know is that R is concave down, and it's important to indicate their interval for 0 less than t less than 12. Since R is concave down, your tangent lines, remember we said concave down, tangent lines are above the graph, which means that you're going to have an overestimate. There you go. Now, in terms of points, they awarded 1 point for your approximation of 30.8. They awarded 1 point for your justification. Sometimes they award points in other areas for other things, but on this particular scoring rubric, this was a 2-pointer. Not too bad. I would expect just about everybody is going to come up with the approximation. This explanation point, we've seen it again and again and again. If you're still struggling here, you need to set aside the time to practice with this. Okay. B. Find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate the units of measure. Rate of change of volume with respect to time, that's dv dt, the derivative of your volume with respect to time when t is equal to 5. Well, we know in part B, or we were told earlier, that the volume is 4/3 pi r cubed. To find dv dt, you need to find the derivative of your volume with respect to time. This is where you need to be careful. The derivative of your radius with respect to time, this is going to be 4/3 pi. The derivative of r cubed is 3r squared times dr dt. dv dt at time t equals 5 is what you're after. That's going to be 4/3 times pi times 3 times your radius at time 5. Your radius at time 5, be careful, that's not 2.0. The radius at time 5 is 30. That's going to get squared. Dr dt at time t equals 5 is 2.0. That's going to be your change in volume with respect to time at time t equals 5. What are the units? You always want to look at this tag here, this derivative expression. How are you measuring volume? Cubic feet. How are you measuring time? You're measuring time in minutes. So it's going to be this number, cubic feet per minute. And I would just stop right there. If you want to know 7,200 cubic feet per minute. Oh my God, I would have completely blown it and lost the point there. 7,200 pi cubic feet per minute. That would be your final answer. Where did they award points? 2 points for the derivative, 1 point for the numerical value, for a grand total of 3 points. Okay, let's keep going. Part C, use a right Riemann sum with the 5 subintervals indicated by the data in the table to approximate the integral from 0 to 12 of r prime of t dt. Then, using correct units, explain the meaning of that integral in terms of the radius of the balloon. Okay, so let me jot down the important stuff here. The integral from 0 to 12 of r prime of t. We're doing a right Riemann sum. And we want 5 subintervals. What's going on with the handwriting there? 5 subintervals. Okay. Well, let's see. We're going from 0 to 12. Now be careful. If you read this too quickly, you are likely going to think, oh, I'm going to go to 0 to 12, I'm going to do 5 intervals, they're going to be equal widths. At no point did we say equal width. They said use the data points from the table. Well, that means we're going to go from 0 to 2, from 2 to 5, from 5 to 7, 7 to 11, and 11 to 12. Your integral from 0 to 12 of r prime of t dt using the right endpoint for each subinterval, how wide is the interval, in this case 2, times the height of the function at time 2, in this case that is 4.0, that's the first one. Second interval, how wide, 3, times the height at time t equals 5, 2.0, plus the width is 2, times the height r prime of 7 is 1.2, width of the next interval is 4, times the height at 11 is 0.6, plus the width on the last one is 1, and the height at time 12 is 0.5. This is a numerical value. There is no reason whatsoever for you to simplify. But if you did, that's going to be 19.3. Now, what does this integral represent? Well, r is the radius. R prime represents how fast the radius changes. How fast the radius changes. And one of the things I really keep pushing my calculus students to think about is when you integrate a rate function, you're changing from how fast whatever's going on to how much. So the derivative here says how fast the radius changes. The integral is how much the radius changes. Now give me the time interval from t equals 0 to t equals 12 minutes. In terms of your units, how are we measuring r prime? R prime is feet per minute. How are we measuring time? We're measuring time in minutes. Feet per minute time minutes is going to be feet. So how much the radius changes from t equals 0 to t equals 12 minutes measured in feet. In terms of how points were awarded here, it's 1 point for the numerical value or for this expression over here. Those are the same. 1 point. 1 point for your explanation for a grand total of 2 points. And if I'm remembering everything correctly, we're up to 7 of the 9 points so far. I think we're doing pretty darn well. All right, one more part to go. Is your approximation in part C greater than or less than the true value? Give a reason for your answer. Okay, so one more time. The integral from 0 to t of r prime of t dt. All right, this one's tricky, and I'm going to admit I kind of cheated a little bit. I looked at my solutions from the first time I did this. Okay, what do we know? What we know is that r is concave down. That's what we were told. If r is concave down, well, what we're looking at is r prime. What do you know about r prime? R is concave down, r prime is decreasing. Okay, well, I don't know exactly what r prime looks like, but imagine for a second that I sketched r prime on the interval from t equals 0 to t equals 12. R prime must be decreasing. Okay, now does it have to look like that? No, of course it doesn't have to look like that. But not only is r prime decreasing, we're using the right endpoint method to approximate your integral here. So you've divided your region, this interval, into 5, and you're using the right endpoint method. Draw those rectangles. What do you notice about every single one of those rectangles? They're all going to be missing some area from the true integral. So I think you know it now. What kind of an estimate are we going to get? The integral from 0 to 12 of r prime of t dt is an underestimate. Now here's where you've got to be careful. It's your justification. If you say it's an underestimate because the rectangles contain less area, that's not going to be good enough. This graph that we did over here, although it is masterfully drawn, isn't going to get it. You have to mention the behavior of the function, because r prime of t is decreasing for 0 less than t less than 12, and we are using the right Riemann sums. Okay, so that is the end of the problem. Sorry, we've got all sorts of chaos going on in the DeRosier house right now. They awarded 1 point for the explanation, and if you get the units correct in B and C, so this is units in B and C, they awarded 1 more point for the grand total of 9 points. That's the end of that problem. All right, let's keep this party going now, shall we? So now I'm on page 85. This is from the 2011 AP exam, Form B. This is question number 5, and of course it's another data table question. Okay, Ben rides a unicycle back and forth along a straight east-west track. Okay, good for Ben. The twice differentiable function, first derivative and second derivative, exist. Function is continuous, all the things, all the nice things. B models Ben's position on the track measured in meters from the western end of the track at time t measured in seconds from the start of the ride. Okay? The table above gives values of b of t and Ben's velocity v of t measured in meters per second. Okay, so b of t is that position? His position, yep. And v of t is his velocity, and of course t is time on this interval. A, use the data in the table to approximate Ben's acceleration at time t equals 5. All right, we are pros with questions like this. We have to be pros when it comes to questions like this. I filmed so many of them. In part A, I want the acceleration at time 5. What's the key here? The acceleration is found by finding the derivative at time 5. Why do we have to approximate? Because we don't actually have a function for the velocity. We have some points from the table. The derivative of the velocity at time 5 is approximately the value that you get by looking at the velocity at time 10 minus the velocity at time 0 divided by 10 minus 0. The velocity at time 10 is 2.3. The velocity at time 0 is 2.0 divided by 10. Stop there if you want to. Simplify further if you want to. 0.3. What are the units? Well, units for your velocity, I can see in the table, are meters per second. Units for the time is going to be seconds. So your acceleration is 0.03 meters per second, or meters per second squared. The College Board awarded 1 point for the numerical answer, and later, if you also get the units correct in part B, they're going to award you a point for the units. But right now, if this is all that you've done correctly, Nada. All right, part B. Using correct units. Aha, I told you, units. Interpret the meaning of the integral from 0 to 60 of the absolute value of v of t dt in the context of this problem. Approximate this integral using a left Riemann sum with the subintervals indicated by the data in the table. Okay, let's pull it all together. So I want the integral from 0 to 60 of the absolute value of the velocity with respect to t. You just have to have this memorized at this point. They ask it all the time. You've got velocity. You're taking the absolute value of velocity, which makes this now speed. If you integrate speed, what you're going to get is the total distance traveled. Total distance traveled. Tell me the time interval from t equals 0 to t equals 60 minutes. How are we going to measure this? Measured in, well, let's go back and look at v of t. v of t is meters per second. Time is being measured in seconds. Those units cancel out. Measured in meters. Great. Now, what did they ask us to do? How did they ask us to approximate the value? They said a left Riemann sum, and we're going to go from 0 to 60. So let me do my time interval again. We're going to go from 0 to 60 using the points in the table above. So at 10, 40, and 60. These are my three intervals. I'm using the left endpoint method. My approximation, length of the interval 10 times the height of your velocity function, or I guess your speed function, at time t equals 0. Well, that's going to be 2.0. That's your first one. Your second interval, how long is it? 30. Left endpoint method, what is the speed at 10? That's 2.3. Your third interval, how long? That's 20. Times how tall? The velocity at time 40 is 2.5. Don't bother simplifying. If you want to, if you just need to know, it's going to be 139 meters. They awarded 1 point for your explanation, so you had to mention total distance traveled. If you get the units of meters and the units of meters per second, had to get it right in both places, they awarded a point. And then the numerical value, so this guy over here or the 139, earned you that third point. So part A was worth 1 point. Part B was worth 2 points. The units in A and B together, the third point. Okay, so let's look at part C. In part C, for the interval 40 less than or equal to t less than or equal to 60, must there be a time t when Ben's velocity is 2 meters per second? Is Ben's velocity equal to 2 meters per second on the interval 40 less than or equal to t less than or equal to 60? And of course, you have to justify your answer. Well, let's take a look. Now, first time I did this problem, I said, okay, what do we know? What do we know about the velocity? Let's see. I know that b is twice differentiable. And well, what does that mean? That means that the first derivative exists and is differentiable. It means your second derivative acceleration exists. Okay. Well, let's see. If b is differentiable, that also means b is continuous. Since v exists and is differentiable, you're also continuous. Acceleration exists, may or may not be continuous. You don't really know about that. And I think that's going to be okay. No, sorry. A exists and is continuous. Sorry, I had a little bit of a brain fart there. Okay, well, what does that mean? We're asking about the velocity having a particular value. If you're thinking about that, like, does the velocity have to be equal to 2? Those are the kinds of questions that I would ask you when you were studying intermediate value theorem. Does the velocity have to be equal to 2 on the time interval 40 to 60? Well, bummer. The velocity at time 40 is 2.5. The velocity at time 60 is 4.6. I know that the velocity has to take on all values between 2.5 and 4.6, but that's all I know. And 2.0 is outside of that interval. So I can't use the IVT. Now, the mistake is some students are going to say, oh, well, that means that the velocity doesn't have to be equal to 2. No, that means that the IVT is not going to get you the answer. What else do you have? Well, I know that the derivative of position is velocity. I know that b of t is differentiable and continuous, which means that I also get to use the MVT. What the mean value theorem allows you to do is look at Ben's position at time 60 minus Ben's position at time 40 divided by 60 minus 40. Well, what did we get there? That's going to be 49 minus 9 over 20. That's 40 over 20. That's equal to 2. Oh! What we're looking at here in this computation is your slope of the secant line. The slope of the secant line for Ben's position is equal to 2. By the mean value theorem, what that means is that your velocity, which is the derivative of position, equals to at least once, possibly more times, but at least once, on the interval 40 to 60. That's what we needed. Where did they award points? 1 point for showing this difference quotient being equal to 2. You have to show it. And then 1 point for the justification. So basically everything else earned you 1 more point for a grand total of 2 points. All right, we've got one more part to go. I'm coming up on 28 minutes. This video is going a little bit long. My apologies, but it's worth it. These are 2 really good questions that I want to make sure you understand. Okay, sorry about that. I just got a message that my computer was full. All right, so part D again. A light is directly above the western end of the track. Ben rides so that at time t, the distance L of t between Ben and the light satisfies this relationship L of t squared equals 12 squared plus B of t squared. At what rate is the distance between Ben and the light changing at time t equals 40? Okay, so let me see if I can draw a quick little picture here. So I've got a light. Don't make fun of me. I am not an artist. That is this is meant to be my light. Okay, here's Ben. What do we know in part D? We were told that the light is directly above the western end of the track. Ben rides so that at time L, the distance L between Ben and the light, so L is the distance between Ben and the light. Here, oh, bummer, I missed it. That's L. Satisfies the relationship L of t squared equals 12 squared plus B of t squared. So L is the distance between him and the light. It must mean that the light is 12 feet tall. B of t is his distance from that point. You've got L of t, B of t, and 12. So that gets us this relationship that L of t squared equals 12 squared plus B of t squared. They were kind. They gave that to you. at what rate is the distance between Ben and the light changing at t equals 40? What they want is dl dt at time t equals 40. What this is this is a related rates question. And I'm going to be filming another video on related rates in a little bit. But with a related rates question, you are measuring how things change with respect to time, which means you're going to have to take derivatives with respect to time. Well, what's the derivative of L of t squared? It's going to be 2 times L of t times dl dt because of the chain rule, equals the derivative of 12 squared, 12 is a constant, derivative of 12 squared is going to be 0, plus the derivative of b of t squared, that's 2 times b of t times db dt. What I want is I want to know what dl dt is at the time when t is equal to 40. So, what do we know? Well, 2 times L of 40. I don't know that yet. We're going to come back and we're going to have that conversation. Is equal to 2 times B of 40 times dB dt at time t equals 40. We got a whole lot going on here. Well, what's B of 40? B of 40 at time 40, Ben's position is 9. Okay, so on the right, we've got 2 times 9. dB dt at time t equals 40. What is that? Well, what was B? B is Ben's position. dB dt is going to then be the derivative of his position. That's his velocity at time 40, which is 2.5. Where we are now is we've got 2 times L of 40. Oh, I just realized I made a mistake. Bummer. Times dl dt at time t equals 40. Man, Jackie is freaking out right now. I understand, Jackie, but okay, here was my mistake. Back over here, I had 2 times L of 40. I should have had dl dt at t equals 40. Please go back and squeeze that into your notes. I'm doing a horrible job. I'm going to fix this. 2 times L of 40 times dl dt at t equals 40 equals 2 times 9 times 2.5. What you're after is the dl dt at time t equals 40. What you still need is to figure out L at time 40. And here's the key. At the moment when t equals 40, there's the light, here's Ben. The light is still 12 feet above the ground. What is Ben's location at time t equals 40? Well, we know that he's 9 feet away. What you need is L of 40, that's this value over here. Because you have a right triangle, 12 squared plus 9 squared, just for now let's call that C. 144 plus 81 is C squared. C is the square root of 225, that's equal to 15. You may have also noticed that this is the 3, 4, 5 right triangle, except multiply all the sides by 3. That 15 is the value of L of 40. So 2 times 15 times dl dt at t equals 40 equals 2 times 9 times 2.5. If you want to multiply it out, that's 45. That means that dl dt at t equals 40 is 45 divided by 2 times 15, which is 30. Simplify if you want to. That's going to be 3/2. What are the units? L, that's the distance between Ben and the light, meters, divided by T, the time, seconds. Okay, my apologies for the mess up here. Let's see, what happened? Where did they award points? 1 point for finding the derivative, 1 point for using the fact that dB dt is actually equal to the velocity, 1 point. And then 1 point at the end for this numerical value. Part D is a 3-pointer, and that is a tough question. But my friends, we are done with this video. Hope you found this helpful. These data table questions are a great opportunity for the College Board to mix everything together.